Last week, we saw how to use filters. So let's finish this part on filters. The idea of filters is you start from a data series. This is the curve in black here. And then you want to extract in a non-parametric way the trend and seasonalities. Here we did it by applying differencing at lags 1 and 16. And this is a time series we obtain, which looks like noise. It looks stationary in the sense there's no clear trend or stationarity. But when we look at its ACF, autocorrelation function, we see there's a strong correlation at many, many lags. It's strong here because it's above the dotted lines here. And one way to address this is to apply yet another filtering step by using an ARMA filter applied to the difference time series. We obtain something that on a trajectory basis doesn't look very different. But if we look at the autocorrelation function, we see that they are very small. You wouldn't clearly see the dotted lines, but practically all the bars are at or below or between the dotted lines. So we have here two steps of filtering with two different goals. The first one is to capture trend and seasonality. The other one is more statistical in nature, is to make the residuals IID. Then, using the calculus of filter that we have seen in the previous week, we're able to go from a prediction in the residual domain to a prediction into the original domain. And this is performed here on this diagram where we see the prediction and the prediction interval compared to what we would do if we do not have the second step, if we look only at the application of the first differencing filters here. We see that the benefit is primarily in reducing the uncertainty about the prediction, the point prediction being already good with the first method. What I want to share with you today is perhaps some of the algorithmic details on how we do exactly this. Fixing the typo. So they are given, as mentioned in the lecture note in proposition 5.4, but I want just here to give you the idea, which should not be new because we saw the use of this already in the past week when we talked only about the differencing filter. It is related to two things, the calculus of filter, and second, realizing that doing a prediction is about computing a conditional distribution. So I recall here the notation. We have the original time series, y. We difference it, we obtain x, and the filter that we applied is called L. And then we're not happy with the difference data, so we apply another filter, or more precisely, we assume that x is the filtered application of a filter to IID noise, and f is an ARMA filter, which I recall implies that the filter and its inverse are stable here. Here there's a difference between those two filters. Differencing filters are not stable in the sense of stability that we said before. So they are invertible. L-1 exists, but the coefficients of L-1 go to infinity or do not decay to zero. So it's just at the boundary, in fact, of stability, which has some implications that we'll see here. When we compute the point forecasts and the forecast intervals, we use the filters in two different ways. The point forecasts are based on this sequence of filtering steps. We say how we get epsilon from y. And I can write this as a filter. I can ask MATLAB for the impulse response of this filter here, and I call it h. And I will write epsilon is equal to epsilon f minus 1L. Epsilon is the filter applied to y, and if I apply this by putting all the y's on except the first one on the left, that gives me this equation here that we have seen many times. It's the one of the ways of using the impulse response, which gives us a recursive way of computing y from epsilon, right? The impulse response gives us how to compute epsilon from y, but it also gives us a recursive way of computing the inverse here. So that's the major function we have. Now, when using this, then we will have the fact that although, L is a stable filter, L minus 1 is not stable, but L is stable. F minus 1 is stable, so this is a stable filter, and because of the F product here that decays exponentially fast, that gives a sequence of terms, H, that become very quickly very small. They decay exponentially. That's the key thing. We need this because if you realize here, we integrate, sorry, oops, there's a fly here in my office. We integrate all the previous data of the past. So we have seen when we talked about filters that we need to be careful about such things. If the impulse response explodes here, there will be numerical problems in this summation here. But here it will not be the case because in practice, there is a large number of terms, but in practice, only the very first terms will have non-negligible values here. And because the decay is exponential, even the summation of a large number of terms will remain small. Now, if we instantiate this, for example, at t plus 1, that gives us this formula, and at t plus 2 is this formula, from where we derive the prediction formula. Prediction of yt hat of 1, this is what we predict for yt plus 1 when we are at time t. So we use this formula. We're at time t, that means we know everything up to time t. So yt minus 1, etc. are known, so they are non-random. And then we need to predict epsilon t plus 1. After many steps of differencing, typically we obtain noise that is zero mean. It's not always the case. If it's not the case, we need to add the mean. But here I'm assuming it's the case. Therefore, the prediction of epsilon t plus 1, or in more precise terms, the conditional expectation of epsilon t plus 1, given all the past, is equal to its expectation, because epsilon is an IID sequence. That's the property of IIDness. And therefore, its expectation, which is 0 here. So when I predict, I simply I predict epsilon by 0 and the rest by their values, which are known here. So that gives one possible formula for computing the prediction at time t for one step ahead. Similar at 2 steps ahead, I will have a similar formula where here, when I am at 2 steps ahead, yt plus 1 is not known. So the conditional expectation of this is the conditional expectation of yt plus 1 given all the past, which is exactly what we had seen in the previous step. So we have a recursive formula for obtaining the forecasts here. This works well if we do it in this way, because the H terms are decaying very fast. If we had done it in another way, there are different ways of using the filter, we might have problems if we're summing up a large number of things. In fact, the other way is what we use for obtaining forecast intervals, but for some reason, the problem will not, will go away, as we will see. If I use the reverse filter, this reverse filter exists, so L minus 1 exists, but is unstable, which means the coefficients will grow. They will not grow very fast here because L minus 1 is just at the boundary of stability, but they will grow, which is annoying, and if we have large summations. But as we'll see, we will use only a small number of terms here. So we can use the filter formula for this representation in this way. So we obtain y as a function of epsilon. We could use that for point forecasts, but that would pose numerical problems. But what this tells us is, for example, that if I look at this summation, if I look at all the terms that are here after time t here, then I see that all the terms that are after time t, when I am at time t and I know everything up to time t, because the filters are causal, knowing y up to time t is the same as knowing epsilon up to time t. So I know all the epsilons here. And therefore, I can write that the expectation, the conditional expectation of yt plus L, given everything I know up to time t, is obtained by setting to zeros all the terms that are t plus 1, etc., because they're mean, their expectation is 0. And the other terms, I need to keep them here. But we can view this in a different way. We can see all those dots here and those terms that are complicated to write and not useful to compute because the terms d grow, but we have a representation for them. Those things are exactly equal to the prediction I do at time t, which I have computed through another formula. But this formula tells us this here. Those two formulas are exactly the same. They tell us that the true random future value of yt plus L is equal to the sum of those epsilon terms that are in the future, plus something that I know already. And the thing that I know already is exactly what I have computed with the point prediction before. And that's the key formula that is used to obtain prediction intervals. For example, when we know something about the epsilon, if we believe that the epsilon are Gaussian, then the sum of the epsilons, because they're ID, is also Gaussian with a variance that's equal to the sum of the variances, which gives us a prediction interval with, for example, 95% coverage, 196 sigma, and 196 the variance of this, which is given by this formula here. So this is, I would say, the classical ARIMA modeling. This is what you will find when people use what they call the ARIMA method and formulas that may be given by packages like MATLAB here. Sometimes we may want to be a bit smarter. Sometimes it's good, sometimes it's unnecessary. In particular, in this case, if I look at the residuals, I could use the formula I said before, but if I look at this and I say this is a Gaussian time series, perhaps this is unrealistic because we see that many values are centered around 0, but once in a while there is a very large value. So that means that probably this time series is, which is the residuals, after all the filtering steps that I've explained before, is best modeled by something that's non-Gaussian. Perhaps we could use an exponential Laplace noise. We could say, well, this is not Gaussian, but this is Laplace noise, and then I could try to fit the parameters here. Or I can do something more brutal, but that is easier to apply, which is to use the philosophy of the bootstrap here. The idea of the bootstrap is, if I am convinced that this is reasonably IID, and this I obtain by looking at the ACF, I take this as a sample of the distribution of the residuals, which is perhaps not Gaussian, but the best I can do is therefore look at the empirical distribution instead of assuming it's Gaussian. And so this idea leads to this pseudocode here. An alternative way to forecast my data is to compute so I have my data, I put little y to make it clear what is in small caps, in small case is data that I have, and what is in capital is simulated futures. So I have my data, y1 to yt. I apply the differencing filter L. I apply also the filter F. For some reason in the RMAL literature, it's always F minus 1. That gives me the residual. Then I compute them once I have fitted the F, and I believe it's a good fit here. And those residuals, this is what I've shown in the previous slide. So this is, now I will treat these residuals as my data. And I will simulate capital R possible futures of my time series. For every simulation of the future, I want to do a forecast up to lag L. So I will draw L numbers with replacements from this bag of residuals. The sequence EQET, which I don't treat as a sequence, but a simply raw bag of values, because I assume it's ID, so the order plays no role here. So I draw L of them with replacement. That's important to generate something that's ID. And I obtain some of them. I call them this epsilon sub R. And I create in this way, this is my simulation of the future in the residual space. So the idea is very simple. If we believe the residuals are ID, it's easy to simulate. And then, since we have filters to go from epsilon to y, that is very easy. I simply apply the filters by computing capital X, such that by applying the filter F that we had seen before for obtaining the residuals. And then also I apply the filter L to obtain the future points of the time series capital Y here. Because the filters are causal, my residual time sequence always, for all the simulations I'm doing, have the same values from the past up to time t here. Therefore, all the x and y will have the same property. So I am truly generating possible trajectories of the future in the x space, and what is really interesting, in the y space here. Then, once I have obtained this, I have, if I'm interested in a prediction at lag L, then I have capital R possible predictions. If I want a 95% coverage interval, and if, for example, I've done 1000 minus 1 samples, I will take I will sort those and take the values of rank 25 and 975. This is a trick we've seen several times. That will give us a 95% coverage interval of the future. So that's the idea of the bootstrap that we're now applying to simulations of the future. I did that for this example here. On the left, those are the prediction intervals I obtained with the Gaussian assumptions. On the right, they are the prediction intervals I obtained with bootstrap from the residuals. We see that they are smaller and in fact a bit better, because the 95% confidence interval should be true 95% of the time. So that means we should have, in average, 1 point out of 20 that is outside or slightly outside, which is exactly what happens with my bootstrap from residuals. So if I want a better, more narrowed forecast, this is one way to improve it. Recap, what do we do when we do ARIMA modeling? Given some time series, we remove trends and seasonalities using differencing filters. And this is perhaps the most powerful step. We've seen that doing this alone gives us already good point predictions. If we care about prediction intervals, which you should, for example, for the lab, if you want to participate in the forecast competition, the value of your forecast will depend on the forecast interval. So if you care about the forecast interval, you need to work perhaps a bit more on the residuals. If your residuals does not appear to be IID, you may use ARMA modeling to make it, roughly speaking, IID. And if the noise appears to be Gaussian, we have seen closed form formulas for prediction intervals, which is very convenient and therefore very often used. Else, we can simulate future trajectories by resampling from residuals. So this is, I would say, the state of the art of ARIMA modeling. Of course, because forecasting is essentially uncertain, there are many alternative methods that are being used. The methods we have seen are forecasting from data alone. When we do forecasting in the energy sector, for example, we typically use other information, which is based on more high-level modeling. For example, we know that if there is a football match on TV on one evening, that is important to a given country, many people will be watching that football match. So we forecast that there will be more power consumption on this evening because of the football match. So of course, if you want to do very detailed forecasts, that becomes a science of its own, and you may need to incorporate a large number of factors. Nonetheless, most methods are based on regression, modeling, filtering, which are all the basic elements we have seen. Because forecasting is so important and becomes more important because of renewable energies that are much more dependent on weather conditions, then forecasting is becoming a business. Therefore, of course, there are many, many more methods. Methods based on machine learning. We can view machine learning as a sophisticated way of doing a regression, sometimes done in a way that we understand well, sometimes done in a way that's more mysterious. We're just at the beginning of this era of such methods. And of course, you can combine all of those together. For example, I will just mention one combination that is also often done, which consists in combining linear regression with ARMA noise. We have seen two methods as two separate, completely disjoint methods. I've shown how to do a prediction by fitting my model, a model with sine functions and polynomial growth, which is one way to do it. and I've seen a filtering method, but of course they can be combined. For example, if you combine them, you could obtain that you model your data series, perhaps after doing an obvious pre-processing stage of removing trends and seasonalities, then you can model it as a regression model, here a linear regression plus noise. And if the noise does not look IID at all, then you can use the ARMA process for the noise and say that the noise is, after all, an F of something which is IID here. Now, the question becomes, how do you fit the beta and the F? And very often you get into the into the world of non-convex optimization. So one method that is the method of choice today is to use the observation that if I know the filter F, I know how to estimate beta. Right? If I know the filter F, by applying the inverse filter, I have this model, which is a standard linear regression model. So I can apply linear regression to estimate beta. If I know the filter F, but the coefficients of the filter, which is an ARMA filter, so it has coefficients that need to be estimated, that are real numbers. Right? Vice versa, if I know beta, I have a model here where I can, or this model here, then my data series become YT minus sigma of this. And then in order to fit this, to find the appropriate F, well, that's what we have seen last week. It's how to fit an ARMA model to some sequence epsilon. And that is this is done using nonlinear and non-convex methods, but that are efficient and work well. So I know how to solve both problems, how to fit beta if I know F, how to fit F if I know beta. So the traditional method for that is to iterate between the two. You start with the best guess of beta. For example, ignoring the fact that epsilon is non-IID, you fit beta, that gives you a first tentative beta. Then you refine the noise, you fit, for this beta, you find an F. And then out of this F, you re-estimate beta by using this formula here that will give you slightly different estimates of beta. And you iterate until you're tired of iterating or until it truly converges here. So that's, I would say, one of the sophisticated methods that's often used when you have sophisticated time series. On the opposite extreme, you have very simple methods that are very often used as well. Here, the problem is a bit different. When you forecast, for example, the renewable energy production that will happen in the 3 hours from now, then you want very sophisticated methods because there's a lot of money that can be lost or gained if the forecast is wrong here. In order to compensate the forecast, for example, you will need to prepare some reserves here, and also the market prices will depend on the forecast. So there's a lot of money at stake, and people use very sophisticated forecasting methods. But forecasting is used also in other scenarios, for example, in operating systems, where you may want to forecast when the memory leakage will become a problem and you need to reboot your server, for example. So for such, in this you can see in one of the quiz where you will have to answer this question. So in this case, you're interested in very simple model. That's the other extreme, because you want to compute them online and apply them online here. So for that, there are models like Holt-Winters or multiplicative ARIMA that are models that are very simple and also have a very small number of parameters here. For example, here for the same time series we have seen before, here I've used two of these models, the Roberts model and the Holt-Winters additive seasonal models. There's a whole zoo of models that are more or less simple, but very remarkable. Our Holt-Winters model that can be simply interpreted in terms of differencing filters. I invite you to look at the lecture notes, but there are very few parameters. The Holt-Winters additive seasonal model has only 2 parameters, 2 real numbers that need to be fitted. And so it's quite adequate to be fitted online. And it gives, as you can see here, at least in this example, excellent predictions. Voila, that's all we'll see in terms of theory. Forecasting is saying something about the conditional distribution of the future, given the past and the present. So like any problem related to distribution that requires making some assumptions that you want to validate as much as possible. We've seen essentially the classical methods. Now the ball is in your camp. For the lab, we're asking you to forecast some energy consumption of EPFL based on measurements we performed in the smart grid project of EPFL. And feel free to use whatever method you want, and we will see what are the best methods when the lab is over. Voila. If there are questions, please don't hesitate to ask now. If no, you can ask the questions later, of course. If no, without further ado, we move on to the next chapter, which is about tests. So what are tests? Tests are the very classical and perhaps the extreme part of statistics. Everybody who does statistics typically uses tests. And if you publish a result of some kind, you may have to do a test to validate what you're doing. So we have to go through it. We must be able to understand what tests are and be able to use them. As I will explain also, we should also not be fooled by tests. Tests are just tests, and they help quantify something, but of course they do not say everything about the data. We have seen situations where we gave very, very heuristic or even very approximate answers. For example, does this data come from a normal distribution? So we look at the QQ plot, the normal QQ plot, and then we see when it's no, the answer is clear. When it's yes, the answer is never really clear. So there is some uncertainty and some uncomfort here because it's hard to say when things are really good enough. So the goal of tests is to avoid that you have the problem of scratching your head and saying, is this good enough or not? The test will take that burden away from you. Another situation, which is sometimes also easily explained, is if you compare two systems and you want to say, is one better than the other? For example, here I've compiled a system and I measure the runtime. Here I put it in log scale. This is a time series we've already seen before. We saw that if we use it, the natural scale, it is far from Gaussian. So I take the log and it looks more Gaussian. So probably all the statistics will work well. And then I have plotted here scatter plots of the results of what we call non-pair data, which means we did 100 experiments with the blue option and 100 experiments with the red option. But the red and blue experiments are not exactly reproducing all the same values because we were not able to do it. For example, this is what happens when you perform measurements on a system that's in production, that's running in the real world. So we have 100 blue results, 100 red results. Because there's a large variability, we don't really see clearly whether red is better than blue or vice versa. And we would like to know because we have to install one of the two. So one way to do it is to look at a confidence interval, for example, for the mean or for the median, because but now that the data looks reasonably Gaussian, both are probably giving similar result. If I compare the confidence intervals for parameter set 1 for this experiment here, then the answer is clear. We see that the performance of option 0 is way smaller than for option 1 here. So in that case, 0 has a small number. So if it's log of runtime, 0 is better here. But here, perhaps it's less clear because the intervals are largely, or for 3, the intervals are largely overlapping. So it is perhaps not so clear here. I mentioned the normality here. Is data normal on the left? We would probably say no. On the right, we'll say yes, but we're not too sure. So we would like to be able to answer this. So to understand how statisticians think about tests, we need to introduce the Neyman-Pearson framework. There are different frameworks. There's also Bayesian statistics, what we will not do here, not because it's not interesting, but because it will take more time. And most of the time when you will read p-values and reports on tests, it will be based on the Neyman-Pearson framework. So that's the one we will see here. It is superficially very simple, but there are subtleties here. So we are given some data set, XY, that's my data here, and a model with a parameter theta, which we believe explains the data. So that should sound familiar to you by now. In fact, statisticians reason about the world as if what they see is generated by a simulator. You've done simulators in the lab, so now you know how to do it. So they believe that the world is done by students who make simulators and produce data. And we know the model of the simulator, but we don't know the parameters used by the student, by the coder of the simulator. That's the mental model of classical statistics here. So we want to reason about the parameter theta, and the test is in fact about theta here. So we assume that there are two hypotheses, one called 0 and the other one called 1, which corresponds to statements we can make about theta here. The set of values that correspond to the null hypothesis, which I call capital theta 0 here, is of course the complement of the set of values that corresponds to the hypothesis number 1. But it's important to realize that in practice, for all tests that are done in real life and that you will see reported upon, they use what is called the nested model. The nested model means that the null hypothesis is special in that we assume that it corresponds to a special case of a more general framework. And the thing we want to test is, are we in this special case or not? Of course, I can in general, and the Neyman-Pearson framework allows it, I can do a test that tests, for example, is the mean of this data series 1, that's my null hypothesis, or is it 100? That would be my hypothesis H1. So I have two hypotheses, I want to test between the two. This is what we do in communication theory, for example, when we want to decode the bit that we have received. Am I seeing a 0 or a 1? Here I have to choose between two binary hypotheses. But in statistics, most of the time we are not in this case. We have a continuous set of values, capital theta, and we're interested in knowing, are we in a subset of capital theta, which is of smaller dimension than the global set here. So the two hypotheses, being null or non-null, are not symmetric in the sense that the null hypothesis corresponds to fewer dimensions than the alternative hypothesis here. For example, if I have the compiler options example I mentioned a few minutes ago, we could view this as saying the data points I see is the output of a simulator that samples from a distribution, I call it capital F, and there are option 0 and option 1. The null hypothesis is the two distributions are the same, and the opposite hypothesis is they are not the same here. So here, of course, that's an extremely general test. Most of the time, we're not able to do tests that are as general as that. But here, that would correspond to saying the set capital theta is the set of all pairs of distributions for blue and red. And theta zeros is the pairs that are equal. So if we are in of course, the set of distributions in an infinite dimensional space, which is not so easy to handle. If I assume that the set of distribution live in a space of finite dimension here, of course, the dimension of theta is twice the dimension of theta 0. Most of the time, what is done is fairly simplistic assumptions about the distributions. For example, if I assume that the distribution is Gaussian, which, as we have seen, requires some care. If here, by rescaling the data in log scale, that is a distribution that is not so violently shocking. But very often, this is implicitly done here. This is called the ANOVA model, analysis of variance. We'll explain why a bit later. So ANOVA means this model. It means I assume that the two data sets I have are independent IID from two Gaussian distributions with same variance, almost stochastic here. The only thing that's different is possibly their mean here. You could argue whether this is a good model or not, but this is the model that's underlying many of the tests that use the so-called ANOVA methodology. Here, to fit that in our framework, the set of parameters are mu0, mu1, and sigma. The set of parameters is all the parameters I know to describe my simulator here. So my simulator is something that has produced the blue and the red dots. So I needed to have the mu0, mu1, and sigma, which is the same for both here. And the null hypothesis corresponds to adding the constraint that mu1 is equal to mu0. So theta 0 is of dimension 2, theta is of dimension 3 here. So that is those two models. Tests use the following language. The critical region of the test is a set of possible data values where we decide that we reject the null hypothesis here. So if the data belongs to the critical region, the test rejects the null hypothesis. So all tests will use this terminology. Of course, when we do a test, in some sense, we have to classify, we need to choose H0 or not H0. By doing that, we can have two types of errors, like in any classification task. The type 1 error consists in rejecting H0, which occurs when we are in the critical region, when in fact it is true. And the size of a test is, by definition, the maximum over all the values of the parameters that are consistent with H0, so that are in the set of parameters theta 0, of this probability. So it's the largest probability of type 1 error that we can do. That's the size of a test. It's a number. The type 2 error is the opposite. It's what we do when we accept H0, so we're not in the critical region, but in fact, H1 is true. The true value of theta was outside of theta 0 here. And here, we don't have one value here. We will see why in a few more minutes. We define here the power function, which is the function that for every value of theta, which is corresponding to H1, gives the probability of this type of error. Ideally, we should have that the size is small, 5% or less, and that the power function is large, for example, 95% or less here. In the Neyman-Pearson framework, we design a test that maximizes the power subject to the size alpha here. And most tests that we will see are called uniformly more powerful. They are tests that have the property that for a given size, there is no other test that have a better power function, which is a very weak statement about the optimality of the test, but that's the only one that is practically possible for many tests. So let's see what this means concretely for a small example. We will do it for this small example, but I warn you that in reality, when we implement tests, we're not able to analyze the test in the way we're doing it, and so we have to rely on the test without being 100% sure of what happens in terms of power in particular. But here we'll do it here. Here, to simplify the story, I assume that I have two data sets, but now they are paired, which means I have done the experiments twice, A and B. And if I want to know whether A is better than B, I can simply look at the difference in performance after rescaling, possibly. So I call Xi the difference in performance, the reduction in execution time. I do this first because it corresponds to something that's often done. It's called paired data. When we have paired data, we can simply look at the difference, which reduces the dimensionality. And now the model, if we use an ANOVA thinking, consists in saying that the data that I've seen is following a Gaussian distribution with mean mu and variance sigma squared. And I want to know whether A is better than B here. Now, my model depends on what I am willing to accept. So here I'm giving a specific model where I impose that mu is larger than or equal to 0, which means that I accept only two things. I accept only the fact that A and B are equal, or A is better than B. I think the rest is not possible. If I think differently, then I should put mu any value. But here I put this constraint. That's my test design. I design it in this way. Having said that, saying that A is better than B means mu is positive here. And if they are not, then mu is equal to 0. So mu equal to 0 means there is no difference between A and B. And the alternative is there is a difference, but I think if there is a difference, it must always be positive. So let's try to design a test. In order to design a test, we need to design the critical region, because the critical region will tell us we reject H0, or this is equivalent, we accept H1. Here I'm using intuition. I'm saying, well, all I have is my data. I have my sequence of data points, X. I want to say, is it plausible that the X comes from a model with mu equals 0 or not, or is positive? Then the idea is, well, if I want to reject H0, it is probably because in average, the X is positive here. So if H0 is to be rejected, that means if mu is positive, the sample average of my data should be larger than some quantity here. This quantity C is a free parameter. When we design a test, we always have a free parameter, which is the size of the critical region, which is depending on the size of the test, of the probability of a given type of error. So that's an attempt I'm doing. I try to design a test of this size here in this form here. And now I need to compute what value of C should I have such that the probability of first type of error is, for example, less than 5% here. So I compute what is the max or the supremum for all values that fall within H0 of the probability of rejection. So this is the probability of deciding for H1 when the true value is theta 0. And I don't know what the true value is, so I take the max of this here. If I do the computation, I compute this, I do the computation, I see that it is given by this formula where capital N01 is the CDF of a Gaussian random variable. But we'll see that because sigma is a hidden parameter here that I don't know, depending on sigma, this value can be as large as we want, as close to 1 as we want here. So the supremum over all values of sigma here gives 1 here. So take-home message, well, designing a test is perhaps something not completely trivial, so we will need to see a generic method for designing tests here. So obviously this one doesn't work. If I do a test in this way, that will give nothing useful because the probability of type 1 error that should be small cannot be made small because of this free parameter sigma. Of course, this is not the test that is used for Gaussian pair data. There is a standard method which consists in being a bit smart. Instead of using the sample average, I use the rescaled sample average, where I rescale by something that eliminates the problem of the unknown variance here. So I take S square n, an estimator of variance. We have seen two, one in n minus 1, the other one of 1 over n, so that doesn't really matter here. So I take this as a critical region. And then if I redo the math here, we will see that this quantity is something that we have seen when we discussed about confidence interval for the mean. We see that the distribution of this tends to be Gaussian standard, mean 0 and variance 1, when n is large at least. So this is approximately, when n is large, something that does not depend on the hidden parameters, sigma, and therefore that can be computed here. So what we have done here, we have found what we call a pivot. A pivot is a statistic, something that is built from the data. We have the x, that's the data. The x appear also in the Sn, that's the hidden, but Sn depends on the data here. But at least approximately, when n is large, the distribution of this is independent of theta here. And because it's independent, I can compute the size of this test. In fact, which value of the threshold C would you give if you want to have a test of size 5% here? So we will conclude this first hour with this quiz. I close the poll in a few seconds. And the correct answer is not 196 like it is usually in statistics, but it is 1649 here. And the reason is for this test, we want this probability to be larger than C, which is a one-sided tail. We want the probability that a Gaussian is larger than something, that this occurs with probability 5%, but it's one-sided, so that gives us this threshold here. If we had taken 196, which is another magic number we see very often, we would have 2.5% probability of being above, which is what we do when we want to have two-sided tails here. Here we have single-sided tail, which is related to the fact that in the model here, we assumed a priori that we will never have mu negative here. The hidden mu cannot be negative. That's an out-of-band information we put into the test. So we see that the threshold values may depend on the complete design of the test here. So in summary, for this test, if I have my data points, I want to decide, is there a significant difference, or is A, which means A is better, truly better than B, or is it quasi the same and the difference is only due to the noise? Then I will compute the sample average, rescale it by the magic numbers we use here, and Sn over square root of n, and then we compare to this magic threshold, which will be in that case 16449. And if it's larger, we reject H0, so we say, yeah, it's true, A is better than B. Well, this is how tests work. Before we continue talking about tests, I would like to say a few words about the mini projects, because the deadline is tomorrow. We have already discussed those points, but I'm repeating them. So the goal is to practice what we see in this course on something that is the size of 2 homeworks, so 4 weeks of homework time. The idea is to use something that you're specifically interested in. So ideally something that you have some knowledge from another course, not this one. If you don't find something in your own projects, you can also use data or studies that have been done in papers, assuming that the data are available online here. And if you prefer, you can also address a methodological issue rather than a case study. Step 0 of this is, which is due tomorrow, is to do a 1-paragraph definition. So in this 1-paragraph definition, you should not answer all the checklist here. The checklist is to help you with your 1-paragraph, but it is in the project that you will define the load and the metrics, the factors, etc. For now, what you really want to address is, what is your goal? What are the main issues? And is it really interesting to do a detailed performance analysis, right? While you will be performing the projects, of course, All the checklist here has to do with what we saw in terms of methodology in the first week. In particular, it's important to use a scientific method to draw conclusions in an iterative way and not jump into conclusions that are seen from an interpretation, not really checked by proper experimental validations here. So the next step is for you now to give a one-paragraph definition. When the project will start a bit later, when we finished with lab 4, when lab 4 is over, then you jump into mini project mode, and we will do an interim checkpoint, intermediate checkpoint on May 11 and 12. So you will need to check to find an appointment with me for this. So the goal of this is to have a very informal discussion of what you've done, so of what you plan to do and already how you've started doing it. So the goal is to check your goals, your technical approach, and also to exercise a presentation. So that should be a short presentation with a target speaking time of 10 minutes. So the goal here is just to make sure that what you're doing is right on track. In particular, it's not too big. When the project is over, you will do a presentation to the whole class, and you will have colleagues as audience. So that's a way to test your presentation skills, because the colleagues that are your audience will be asked questions. I will ask them questions about what you presented here. So you must be sure that what you present is understandable by your colleagues here. Based on the past, a list of projects we've seen in the past, be sure to prepare a first slideshow for the private defense and listen to feedback received. So sometimes there are obvious things that are going to cost you too much time, or you're off track. So be ready to receive feedback at the first interim meeting if needed. The first interim meeting, I call it a private defense, in the sense it's just a meeting with you and me. Just to give feedback, and it doesn't count for the grade, and it's not public here. This is a performance evaluation mini project. It's not a master thesis, so you're not supposed to spend weeks doing simulations. So ideally, you should have something that is already prepared. Most of the time, it's not exactly possible, but the development time you need for doing this mini project should not be huge. So the main part of it should really be to do the performance analysis. So if you have huge coding work or instrumental work in doing a simulation, then it's not a good mini project definition. If you base your project on papers, then that's probably obvious, but it's not useless to repeat it. It's not because something is written in the paper that it's true. So it's most of the time mostly true, but the mostly makes a whole difference. So now, also based on past experience, some recommendations about doing graphics. So performance evaluation is about knowing the statistics and knowing the technology to do simulation. But it's also about presenting things, digesting things, and presenting them to an audience, things that are quantitative, so they're not so easy to present. So it's important also to spend some time on thinking on how you want to present things here. And there are classical traps that should not fall in. For example, what's wrong with this graphic? And we see exactly unanimity about what is wrong. And that's exactly the point I'm trying to make here. Exactly. The axis doesn't start at 0. So there are many ways to make a graphic misleading. You should detect them, and you were able to all detect them, but you should also avoid them. You should not be misleading here. Here, of course, it was not starting at 0, so the black bar of the second graph, you seem to be way much better than it is in reality. It is better, truly, but the difference is not so large as it appeared to be here. So scientific honesty is, of course, important. But there are also ways to perhaps better compress the information. Sometimes we've seen spider plots Here is a variant of a spider plot where I plotted the two metrics, because there are two metrics here, Brown energy and cost. Here they were plotted as two different values here. I have exactly the same information there. Perhaps it's harder to read, but perhaps it gives also more information. For example, here large is bad, so something is non-dominated if there is nothing below and on the left of it. So we see that green DC and baseline are non-dominated, but baseline is probably only marginally better in terms of cost than grid DC. So here there's an obvious winner, that is green DC, and we see by how much and how. I'm not saying that you should do graphics like the one I'm proposing here, but I'm saying to you, think about how you present things, because there are ways that are very, very expensive in terms of real estate. Here I'm using a lot of space for relatively little information as opposed to here. Chinese saying, since one graphics is worth 10,000 words. So all the information you put in graphics has much more weight than all the words you can put. So putting wrong messages through the graphics is something to be avoided. Voila, that's what I wanted to share with you about the mini project. So I invite you to upload a short paragraph explaining what you plan to do. I will read it, and I will probably send you comments. Comment I usually have is I might be concerned whether doing all the simulation, all the measurements requires developing a lot of development time or not. So I'm looking forward to seeing all your projects. In the past, that's been an extremely interesting experience for the teachers of this course. Voila, so let's return now to the hard science and perhaps less fancy, but important of tests here. So we've seen how to do a test for this academic example by defining the rejection region. And we've seen that if I want a size of 5%, that is a probability of type 1 error of not more than 5%, I need to put the threshold at the value that we've given here, 165. Now for this test, we should also look at how bad the type 2 error is. So the power function here. So the power function, which I recall is defined as the probability of rejection, that means probability of deciding for H1, when the true value is in H1. So ideally, it should be close to 1 here. If we do it for this test here, we find this value here. Approximately, if I do the central limit approximation, I will have that is 1 minus the CDF of a standard Gaussian, C, which is the threshold we have chosen before, minus this quantity here. And we see that it does depend on the parameter theta. Remember, the parameter theta here is mu and sigma. We want to test whether mu is 0 or not, and sigma is a nuisance parameter here. What I did, I plotted here as a function of mu the value of this power function. For sigma, I approximated by Sn, which is the standard thing we do when we when n is large. So I pretended sigma is exactly equal to Sn, and I obtained the following plot here. As a function of mu, I have the power function. And we see that when mu is 0, the probability is 5%, which is very small, because that's the probability of deciding for H1 when the true value is H1 here, when mu is an epsilon larger than 0 here. Why do we find precisely 5%? Well, it is because we've chosen the threshold C such that the probability of the other type of error, which is a probability of deciding for H1 when mu is equal to 0, then this probability is exactly equal to 0 to 5% here. But because the power function is a continuous function of mu, of course, when mu is very close to 0, not 0, but close to 0, then the value is very close to 5% here. So the bad news is that it's impossible to have a power that will always be 95%, for example, with this nested model. If we want to test whether mu is equal to 0 versus mu is not equal to 0, we have a continuous parameter mu, it's impossible to have both probabilities of errors very small here. If we plot versus mu, we see that there is a gray zone. There's an entire region where the power is less than 95%. So if I want a test that is balanced, ideally, I would like that the power is at least 95% when the size is 5% here, so because both error probabilities are 5%. But for this nested model with continuous parameters, it's not possible. But the consequence is that if mu happens to be in this zone here, the power will be very bad. If mu is, the true value of mu is in the gray zone, the test will likely declare that mu is equal to 0. Now, for the specific data that I had in the example I gave, I can compute the power, and I found that it's very, very close to 1. So the type 2 error is less than a fraction of a percent, which is this very small value here. But this is for this specific data. I cannot guarantee that my test will always have such a high power here. So we can interpret this gray zone as the statistical significance of the test. If we choose a size 0.05, then the test is unable to distinguish 0 from this mu star. This mu star here, this value is 18 here. That means that this test makes sense if 18 is a truly small value for the physics of my system here. In other words, the statistical significance of a test should be matched with the physical resolution of the data. Is my data, if 18 is not something minuscule, then my test is perhaps unbalanced. In general, I could try to balance my test. For example, if I have an optimal resolution, although my parameter is continuous, but in practice, we can still declare what we think small means. If we think that small means 10, then the optimal threshold should not be the one we had before. And if we want to have a balanced test that gives the same probability of error when we're above the critical resolution, or of type 2 error and of type 1 error, then that forces us to have a type 1 error that is, for example, 17%. So if the resolution of what we care about is 10 milliseconds, then we should do a test of size 17%. Right? So there is a relation between the size of the test and the physical resolution of the data that we have, at least in theory. In practice, it is very often forgotten. And this is one of the limitations of this framework. Very often we do a test based on the size, and we are not 100% sure what will happen to the power. I spoke of the size of the test, but if you use MATLAB or other packages, most tests will return what is called a p-value here. So the standard way of using a test is to compute a p-value. So what is a p-value? Well, if we look at the previous example, we had rejection region, this here, and I called T of X the magic formula, the pivot. You remember there was a formula that said I compute this, which I rescale appropriately, because if I don't rescale, I'm unable to create a test that has any reasonable size. So I rescale, I obtain this pivot. This is called the test statistic. And I reject H0 if the test statistic is larger than some threshold here. Right. So the test consists in computing from the data the value which we call T of the test statistics, and to see whether it is larger than 1645 here. But because we know the distribution of the pivot under H0, when H0 is true here, we know that it is Gaussian with value 0 and sigma square. Then we can do the following. Instead of looking at the T value, we look at probabilities, which can be interpreted as follows. Assume I do a hypothetical replay. So I So I have obtained my data, I call it little x. And my data comes from a model. And I assume that someone else replays another data set, capital X, from the same model, assuming H0 is true. So if H0 is true, that means we set mu to 0, and sigma is something that we don't know. And we want to compute what is the probability that the test statistics for this additional hypothetical test would be larger than the value that I have, the one I have from my data. Now, because T of X is a pivot, pivot means this probability, we can compute it even if we don't know sigma squared. So I can plot it, it's 1 minus the CDF of a standard Gaussian distribution. So we'll have a curve like this, it goes to 0 when T goes to infinity, so it's a decreasing function. And saying that T is larger than the magic value here is the same as saying that on the y-axis, we are at or below 0.05, which is the size of the test here. So that's a very complicated way of saying how I have computed my size test here. So the statistics, the value here, 1645, was computed from the fact that we wanted 0.05. That's the quiz I asked just before the break. Now, instead of fixing 0.05 and saying, I say reject when I am above this magic threshold, instead of this, I could compute the value that is on the y-axis here. That is called exactly the p-value. So the p-value is the probability that another hypothetical replay experiment would produce a test statistic larger than the value I have now when H0 is true here. And the rejection region can be formulated as the test statistic is larger than this, or equivalently, it can be formulated as saying the p-value is smaller than 0.05 here. The difference is that now, when I give the p-value, I don't need to specify what is the size of the test here. Here, the test I had formulated had this magic number that was valid when I decided the size is 5%. But we don't really know what the optimal size should be. So because of that, we remove the need to know the size and we give only the p-value. And then how do we use the test? The software package will return to me a p-value, and I know that I am in the rejection region if the p-value is small. So mnemonic is reject H0 when p-value is small here. Now, what small means, certainly smaller than 0.05 in practice is very often the threshold used, but very often we'll see that the values are much smaller. So what I presented was for a specific test, but in general, for any test, we can always reformulate the rejection region by appropriately redefining the test statistics, and the same reasoning can be done. So the test in practice will return a p-value rather than a rejection region. For example, in the case we gave before, the p-value is 1 minus the CDF of the Gaussian distribution times the test statistics, which is exactly what we have plotted here. So another way of visualizing this test is to say I have the data X, I compute X bar, I compute Sn, I plug this into this formula for the p-value, that gives me the p-value. If p is very small, much less than 1 or 5%, I decide that I reject H0. Voila. So here is a small statement I submit to your examination. The critical region of a test has the form test statistic larger than C, where T is a pivot. X is a random vector having the same distribution as the data. What do you think is a valid statement for the p-value? close the poll in a few seconds. And the correct answer is A and B. Well, B is the definition because it's a pivot, so the distribution does not depend on it. And therefore, because it's true for any, then it's true also for the supreme number here. But there is an interesting consequence of this. When we have a pivot, which is typically what we try to do, designing a test is in practice done by finding a pivot or an approximate pivot. Then for a new replay experiment, the test statistic has a distribution under H0 that is independent of the unknown value of the parameter when H0 is true here. So in such cases, the p-value which is equal to this, is equal to this for any theta that satisfies T0. Now you may remember when we studied sampling that the CDF, when we apply a random variable to its CDF, we obtain a uniform random variable here. So the distribution of this is uniform here. So 1 minus between 0 and 1. So 1 minus this is also uniform between 0 and 1. In other words, the distribution of P star of X is uniform between 0 and 1. In particular, whenever theta is in H0, is in theta 0, whenever H0 is true. It means that the probability that the p-value is less than alpha is exactly equal to alpha. So another way of viewing the p-value is to say, if I have a method of computing the p-value, then the rejection region is simply given by P star of X less than alpha, which is what I said informally a few minutes ago, but here is the proof here. Exactly. Voilà, so because of that, p-values are the language that is used practically always when we speak of tests here. What we will do now is to describe two things. First, classical tests that you're very likely to encounter, but also a method on how to generate tests in general, if you have to do it a test, if you have to do and how those tests were generated. So the classical method, if you want the factory of tests, is the likelihood ratio here. Likelihood ratio gives us a systematic method to define tests, and that is in practice found by many tests here. So again, I am in the Neyman-Pearson framework and the nested model. Neyman-Pearson means I have H0 versus H1. A nested model means that H1 is not H0 as opposed to a discrete alternative here. Then we can recycle everything we know of estimation theory. I can estimate theta assuming H0 holds. So if hypothesis H0 holds, that means I put the restriction on the hidden parameter that theta is in the set theta 0. If I do this, I can do an estimation. And as we have discussed several times, for example, when we talked about the IKK information criterion, or when we discussed approximate confidence intervals for regression models, it is useful to know the log likelihood of the data. So I call L sub x of H0 the log likelihood of the data of H0 to recall that we did it assuming H0 is true, and sub x to express that what I've computed here is a result of the data that I've obtained. Remember that when we estimate things in the maximum likelihood framework, the data is given and we optimize over the parameter theta here. I can do the same thing under the bigger model here. This is where the nested model plays a role. Here I'm assuming that theta 0 has smaller number of dimensions of theta. That means that if I optimize over H1 or if I optimize over theta, it will practically give the same here, because this is a region that has negligible volume within capital theta. So what we call, in fact, the log likelihood of the data under H1 is the log of the maximum likelihood when we remove the restriction of theta 0 here. That's a subtle thing, right? We're not really able to find the maximum likelihood estimator under H0, because if theta 0 is typically closed and bounded, so compact, H1 is not a compact set. So the optimization problem usually may not have a solution. The solution may be on the outside of H1, or there might not be an optimal solution inside H1. So we can do the two things. We can estimate the model assuming H0 or not assuming H0, and we obtain two different likelihoods. Of course, the difference will always be non-negative. Why is that? Well, because I have optimized here by putting more constraints. Under H0, I put more constraints. Under H1, I just assume theta takes any possible value. Here I add constraints. So if I add constraints to an optimization problem, the objective cannot be larger. It can be the same if the optimum is in theta 0, but in general, it will be smaller. So the difference here is non-negative. And the idea of a likelihood ratio test is to say the amount of this difference tells us how true, how likely we are that H0 is not true, right? If H1 is true, if the true value of the parameter is not in theta 0 here, when we estimate the model by forcing the assumption that theta 0 is true, then we should have an optimal that is very far away from the true optimal. And therefore, in terms of likelihood, that should be translated here. That's the intuition that's behind the likelihood ratio test here. So a likelihood ratio test is a test that says, I compute those two likelihoods, and I set a threshold. My rejection region is if the difference is large enough, then I reject H0. The difference is large enough, so if I optimize assuming H0 is true, I obtain something that's very different than if I don't assume H0 is true, so probably H0 is not true, because the maximum likelihood estimate does not give a value that is in theta 0. Of course, we need a non-zero threshold because the estimation never provides the exact hidden value of theta. So that's the general form of a likelihood ratio test, and the test statistic is called the likelihood ratio statistic. Why is that interesting? Well, we'll see that there are many, many cases where the test statistics will provide a pivot, or at least approximately, so that we are able to compute everything for such tests here. But before getting there, let's revisit the example we saw before. Before, I had this nested model where mu could be 0 or non-zero. Let's compute the likelihood ratio test for this model here. So step one, I want to estimate, I establish the formula for the log likelihood. Well, my model here, which is a simplistic model, assumes that my data is ID from some Gaussian distribution. So that's the classical formula I would have for the log likelihood. And now I would need to do two estimations. I will maximize this under the general model and under H0. So under the general model, that's similar to something we've seen several times when we talked about mean square and regression model. We want to minimize this. We find that the maximum is, now it depends whether x bar is positive or no, because we impose the restriction that mu is 0, but with elementary means, first by setting sigma, for example, we find that the optimum is the mean. If the mean is positive and if the mean is negative, the optimum mu1 is 0. And the sigma estimate is given by this, the mean square error, with respect to the estimated value here. It's not entirely obvious, but you have in the lecture notes all the technical details to do the computation. It's all elementary. Therefore, if I plug those values of mu1 hat and sigma1 hat into this, I found the log likelihood under the global model to be this. Right. the magic thing is that we see that the log likelihood has only the estimated variance, which can be interpreted as the residual. That's the residual error. That's the error that remains in the model, the average error, once we have estimated mu to be mu1 hat, and the xi are of course not all equal to exactly mu1 hat. So that's the residual error. So same thing, when I impose that mu is equal to 0, that means I impose h0 to be true. I have to redo the same exercise, but now it's easier because mu is known, it's 0. So I have to optimize only with respect to sigma. And we find that the optimum is found here, which is the same formula than here when we had imposed the estimation of mu to be 0. And then the log likelihood is simply the difference of those two formulas. So there are many terms that go away. The ugly terms in log 2 pi, etc., they disappears, and we find that the log likelihood ratio is simply minus n log sigma 1 hat plus n log sigma 0 hat. So we see that what matters is what is the difference, or even the ratio, between sigma 0 hat and sigma 1 hat. Sigma 1 hat being the residual error under the global model versus the residual error under H0. This is an example of something called analysis of variance, which typically has to do with having Gaussian IID random variables as model. We see that everything is captured by the difference in the square residual errors here. If the residual error here under sigma 0 is very different from sigma 1, then the log likelihood ratio will be large, otherwise it will be small here. So the rejection region, if we want to use the generic term, the generic form of a likelihood ratio test, will say when the difference of likelihoods is larger than some threshold, I will say that I reject, which is, after some massaging, it's equivalent to saying that the ratio of the two sigmas is less than some threshold. Since we still don't know what is K, I just give a generic name, capital K, to this. And if we come back to the closed form of those two expressions, and we spend a lot of elementary algebra, we will see that this is equivalent to saying exactly this form here, that the x bar is larger than some threshold you see here that needs to be computed. In other words, we have seen that the likelihood ratio test here is exactly the same test as we have done before by heuristic means here. In particular, we will have the same value C if we want to have a 5% size of the test. So that's good news, and that is showing that this seemingly complex way of defining a test here, in fact, makes a lot of sense, because it gave, at least in this case, exactly what the intuition was leading to. But as we will see, it has also a virtue, is that it will typically give a pivot. Let's, by curiosity, redo the same thing when I do not assume necessarily that mu must be positive. So I ask, is A better than B? When I did that before, I made the implicit assumption that the only things that are possible is both A and B are the same, or A is better. But now I do another thing. I ask, is A different than B? So that's called a two-sided test. The previous one was called a single-sided test. Of course, which one we do depends typically on out-of-band information. We believe that it's impossible, in the previous case, that A was worse than B, for example. But here we don't know. So here we just want to say, is A different than B? Then the only difference is that in the capital theta, we don't impose the restriction that mu is positive. And now we want to test mu is 0 versus mu different than 0. So the H0 is the same, but the H1 is not the same. H1 was mu larger than 0. I can do the same as before. I can compute the maximum likelihood under H1 and under H0. I skip the details. They are similar to what we do before. We need to look at the square, the quadratic function, find the optimum, and we will find here something that sounds familiar to us. The optimum is obtained exactly when x bar when mu, the estimation of mu is the sample mean, and when sigma hat is 1 over n minus 1, the estimate, the sum of the quadratic errors here. And the rejection region is when the absolute value of the test statistic, which is this rescale here, is larger than some threshold here. So not surprisingly, we see that the rejection region here is two-sided, or if we want to make it the standard form, we have to put the absolute value here. And if we want to find a single-sided test here with n equal 100, the eta that we find is 198 or 196 if we would do the Gaussian approximation of the student distribution, as opposed to 165 that we had before. So this means that by changing the H1 hypothesis, the alternative hypothesis, we change the way we compute the p-value here, or at least the rejection region here. By the way, for this test, what would be the p-value, which would be the standard way of describing the test here? I close the poll in a few seconds. Now we have a split between two answers. Admittedly, this was a more tricky question, but let's apply simply the method we saw before. The test statistics, I take it as absolute value of T of X. And the test consists in the rejection region is when this is larger than some threshold here, right? Whoops. The p-value is the probability that another replay experiment would produce absolute value of T of X larger than T, where T is my value from the data, right? Now, because capital T of X is a student distribution with parameter n minus 1, that's a pivot, which is approximately a Gaussian, but if we want to be very accurate, which most of the time we don't, but if we would like to be very accurate, we'll say student instead of Gaussian. Then that's the probability that the absolute value of something is larger than T, but because it's symmetric, is the sum of the two tails probabilities here. Therefore, this is 2 times the probability of being larger than here, which is given by this formula, where little t of n minus 1 is the CDF of the student distribution, which is practically the same as the CDF as a Gaussian distribution. So that is the value, the p-value of this test here, which is what would be returned by any software package here. So as we have discussed before, we see that the H1 matters, even though to compute the size of the test, we use only H0, but H1 matters through the shape of the rejection region. So the nature of the test statistics, in one case we had absolute value, in the other case we did not have absolute value. So therefore, H1 is implicitly present in the form of the rejection region, something to remember. Last, I will conclude with this little observation. Instead of testing whether mu is equal 0 versus mu different than 0, we could have already answered the question by computing a confidence interval for mu. Right? We have received some data, 100 data points. We believe they come from a normal distribution. This is my formula for a confidence interval. I have 198. If I truly believe the data is Gaussian, if we want an approximate formula, I would have 196 here. So this is my confidence interval. Right? So a poor man's test or a naive test would be to say, I'm not sure whether the difference is 0, so let me compute a confidence interval for the difference. And if 0 is in the confidence interval, then I say, yes, it's possible that mu is 0. If 0 is outside the confidence interval, I reject H0 here. So we reject mu when this is true. Well, it happens that if you do that, you do exactly the same as the two-sided test. And this is quite general. If you have a confidence interval for one parameter, or for a linear combination, or for a linear or nonlinear combination of the parameters, and you want to test whether this function of the parameter is equal to some specific value or not, then you can simply compute the confidence interval for this θ1 or for this combination of parameters and see whether the θ0 is in this confidence interval or not here. So take home message, if you are in such a situation, then compute the confidence interval instead of a test, because the confidence interval tells you much more. It gives you not just whether it's 0 or not, but how far you are from 0. So that's one example where full estimation is superior to just tests here. But we'll see there are examples where full estimation is too complicated. For example, if you want to decide whether things are independent or normally distributed, and there we will still rely on tests. Voila, that's the end for today. I'm looking forward to receiving your mini project definitions. And in the meantime, I wish you a good time and good end of day.